So, atomic structure. So we're going to be examining several different models or theories of atomic structure. Um, there's something with each of these theories as we progress through history. There's something that was right about each of them, but there's also something that was wrong about each. But the next one will kind of build on it, so we'll talk about each one. So we're going to start with the Greeks and in ancient Greece here. So Democritus came up with this idea, and the idea was if you've got something, a pile of something or a brick or a piece of paper, and you take that piece of paper and you cut it in half. All right, what have you got? You got two pieces, two smaller pieces, right? If you take one of those pieces and you rip it in half again, you now have an even smaller piece, and you do it again, and again, and again. What's going to happen? You're eventually going to get to a point, especially if you have stubby fingers like Mr. Villa, where you can't rip it anymore. It's going to be super, super tiny, right? Tinier and tinier. Now I'm getting to the point where I can barely even rip that anymore. So I've got a little teeny tiny piece of paper here. Now if I got out a microscope or a magnifying glass and a little scalpel, I could probably cut it up a little more and a little more and a little more, right? And then if I got like a laser and a microscope, a really powerful microscope, I could cut it up a little more. But am I going to reach a point where I can't cut it anymore? Yeah. And if you're doing that with something else, like a pile of sand or a brick or whatever, and you keep cutting it, you're going to reach a point where you can't cut it anymore, right? Especially with the tools that we have. Well, Democritus here came up with the idea that if you take something and you keep cutting, you're going to reach a point where you can't cut it up anymore. And this was the first kind of idea, first bit of particle theory, where you have these little teeny tiny particles. So Democritus said you're going to have these little teeny tiny particles that you can't cut up anymore, and that part of it was right. We call them atoms now, and that's where the word atom comes from. It's the Greek word for meaning uncuttable. All right, but he wasn't entirely right. So we're going to look at the next theory. That was Dalton. So the problem with Democritus was that his theory said that all the little particles that made up everything were exactly the same. So we know that how many naturally occurring elements are there? 92. They didn't know that in 1800 with Dalton here, but they did know that there were some different ones. So with Dalton, his next step in this our particle theory was that there are different particles, that they're not all exactly the same. So he kind of took Democritus and went a step further. So that was a really important step. So he came up with a few things here. So Dalton still had the atoms as being little tiny spheres, little solid spheres. And he said that the smallest particles of an element, atom, they still have the same properties of the element. So if you have a big block of gold and you have a single atom of gold, it's still going to have the same properties. So, but once you go beyond that, then it won't have those properties anymore. And then kind of it's an important statement, but it sounds a little silly. All atoms of a given element are identical, and therefore atoms of different elements are different. Sounds kind of silly to say it out loud, but it was a really big idea, a really big part of Dalton's theory, so really important there. So Dalton was wrong about a couple of things, and there were some problems. So in the 1800s, just after Dalton, some scientific discoveries showed that there were actually parts to an atom, and that you could take away some of those parts. So you had positive parts called protons, and negative parts called electrons. I don't know why they called them electrons instead of like negatrons or something like that to make our lives easier, but they're electrons. So J.J. Thomson came up with a thing, because with Dalton they were solid spheres. So if you have a solid sphere or something, you can't take out parts. So that was a problem. So J.J. came up with a new one to try and fix this. So JJ came up with a model, and it's called the plum pudding model. Plum pudding apparently was very popular in the 1800s. So if we made a model of it today, we would likely call it the chocolate chip cookie dough model or something like that. But back then, it's the plum pudding model. Okay, so what JJ's model says is that you've got this big chunk of positive material, and that would be like the pudding or cookie dough. And then you have these little negative bits, these little negative chunks. And the idea was that in order to be able to separate them, to account for being able to separate them, you could pull those out, just like the plums in a pudding. So that was Thomson's model, and that accounted for being able to separate these things. Okay? Unfortunately, Thomson wasn't entirely right either. So we went another 100 years or so, and we got to Rutherford. Okay, so Rutherford did the gold foil experiment. So basically, this is the slide you won't be able to copy down because it's a little animation. But basically what he did is he had an alpha gun that shot alpha particles at a piece of gold foil. Now gold foil, one of the properties of metal we know, it's very malleable. So gold foil you can actually make really, really thin. So he had a piece of gold foil that was almost 1 atom thin. It was very, very thin. So when he shot these alpha particles, now it looks like a laser here, it's not like an actual laser, just so you're all aware. But he would shoot these alpha particles at the gold foil. Now what he was expecting to happen and what actually happened were two completely different things, and this is why we had to completely change the particle theory. So I'm just going to switch over to something I can draw on here. So under the old JJ model, where you had these big atoms that were just kind of big globs, a single atom would look something like this, right? With a whole bunch of negative bits in it. And then what would another one look like? Well, you'd have another one kind of right beside it. So if this was gold, you'd have like 1, 2, and then another one right beside it. So you'd get something that would look like that. If this were a strip of gold foil, you know, kind of like that, 1 atom thick, okay? So then you've got your alpha particles being fired from a gun over here. So the alpha particles are going towards the gold foil. So what should have happened using this old model? What would happen to all the alpha particles? Yeah, they'd bounce off. They'd go back off in this direction here. Some would go, you know, right back at it. Some might angle a little differently, but they would all kind of bounce back. That's not what happened when Rutherford did his experiment. What happened was most of them went right through. So he didn't understand what was going on at first. He said, well, if we've got these solid atoms, how can they all be going right through? So he came up with a whole new model. So under the Rutherford model, most of an atom is empty space, and most of its mass is located at the center in the nucleus. So it contains the positive protons, and there was a new particle called the neutrons, which they had to come up with to account for all of the mass. They were neutral, so they didn't have a charge, they had mass. And then you had the negative electrons orbiting out in the space around it. So if you kind of picture our solar system, you've got the sun at the center of our solar system, and then you have the planets kind of orbiting around, but mostly it's just big empty spaces, right? So that's what the new model there was like. So if you go back to the gold foil experiment, so with the gold foil experiment, rather than having this, with the new model, you've got very, very small, heavy nucleuses. And then you've got an electron orbiting. Now the dotted lines aren't actually like shells or like there's nothing there, that's just showing the path of an electron. So you've got maybe some electrons floating around in empty space. So now when you've got your alpha gun over here and you start firing particles, well, most of them are just going to go right through, right? Because there's lots of empty space. You might get the occasional one that would hit one of the nucleuses, and then what's going to happen is it's going to bounce back. But most of them are going to go right through. Yeah?
What happens if it hits one of the electrons?
One of the electrons, it would get a small deflection. And it wouldn't be as much as if it hit the nucleus. And you're going to see why when we start talking about atomic mass. All right? Which is a couple slides from it. But yeah, there would just be a minor deflection. And that's because the electrons are really, really small and really, really light. Okay? So it'd be like if you were to run into me, there'd be a big deflection. But if you were to run into like a little baby, there'd be just a little deflection. So I'm just trying to go with different masses, okay? So like I said, all of you should have this already from your research project that's due on Monday. Atomic number is of an element is the number of protons in that atom. So an atomic number is equal to number of protons. So hydrogen, which is atomic number 1, has how many protons? Just one person answers? 1. The number of protons in a nucleus makes an atom different from each other. So hydrogen has 1, helium is atomic number 2, it has 2. And the number of protons in an element never ever changes. So hydrogen is atomic number 1, it has 1 proton, it will always have 1 proton. It will never have 2 protons. It will never have 0 protons. It will always, always, always have 1. All right, so atomic mass. Yes, you should draw this little symbol here, this little picture. Mass number of an atom is the number of protons plus the number of neutrons. All right. So you notice atomic mass is number of protons plus number of neutrons. What's missing there? Electrons. We don't count the electrons. Why do you think we don't count the electrons? The electrons have no mass? No, that's their charge. They have a negative charge. They orbit around, but they are still parts. So that's a good thought. Well, the reason why we don't count them, girls, is because they're really, really, really tiny. All right? So to give you an example, let's take a look at me. I'm not really, really tiny. And I've got a little piece of metal here that's really, really, really light. So let's say that I am the proton, okay? And this is going to represent the electron. So if I go home and I go to the bathroom and I get to the bathroom scale there and I stand on it, it's going to say something like 200 pounds, right? So I'm going to look at it. I'm going to be a little bit sad for a second. And then I'm going to go, wait a second. I forgot. I brought this home with me. It was in my pocket. So I'm going to take it out of my pocket and put it on the counter. And then I'm going to step on the bathroom scale again. Is the bathroom scale going to register anything different? No, probably not. Probably not. It's still going to say close to 200 pounds. Okay? So my point is that this, when looking at the total mass of the system, which is me and this is insignificant. This does have mass, though, doesn't it? Yeah, like we could get out a more sensitive scale, we could measure this, and it would have some mass. But it would not have a significant amount of mass when compared to me. All right? Because I'm so much larger. It's the same with the particles. The protons have much, much, much more mass than the electrons. So we don't count the electrons because they're so very, very tiny. Okay?